Good afternoon. Welcome to the workshop on CADRE. I'm Patty Mabry, one of the organizers of the conference of the workshop. We actually have two parts today. Okay. We have a recorded. This is being recorded. I just wanted to make sure everyone knows that, so that you will be able to use your microphones. So our workshop is on CADRE, collaborative archive and data research environment that we've been working on for the past almost year, but it feels like longer because we've prepped in advance. So I'm here to welcome you. I'm trying to get this to move down and it won't. Is this the right? Down. Can't move slides. This? It won't move my slide. I did.
Yes, you can.
Thank you. So first we'd like to acknowledge our funders. So we have a grant from the Institute for Museum Library Services, and you'll hear more about that later. And Clarivate Analytics, the Web of Science group, has provided the funding for our fellows to travel to the workshop. And what is CADRE? So this is a dream we had that is being realized. About a year and a half ago, maybe a little longer than that, we responded to a solicitation to build a national digital platform. And our central tenet was that academic libraries are challenged to provide sustainable, affordable, and standardized data and text mining services for licensed big data sets, as well as open and non-consumptive data sets that are too large or unwieldy to work within our existing library research environments that have no commercially viable data mining interface. We recognized this need because we were ourselves hosting the Web of Science, and in fact, Connie Warner, who's our keynote speaker, organized a group of us that were all using Web of Science data from different universities to get together and she tried to spark some of this interest in sharing resources. But it wasn't until this grant came along that we had the funding to be able to do that. Also at IUNI, which is Indiana University Network Science Institute, where I was before I left to go to Health Partners a few months ago, we were already hosting the Web of Science on servers for our own university, and I knew that our IT team had the capability to go into the cloud. And we had also just partnered recently with the Big Ten Academic Alliance libraries from other research universities to purchase the Web of Science as a group. And I knew that many of them who had, even though they had purchased it, didn't have a way to host the data and do all of the requisite things that's needed to actually use the data. So they had purchased it and was sitting in a black shelf somewhere, wasn't being used. And part of it was that they didn't have the expertise and they didn't know how to do it, but it's also costly. So the idea is that we have a shared resource for researchers. This is the libraries chip in together to provide a shared resource for researchers. We also have a free tier, and you'll hear more about that, to solve these issues of cost. Also siloing, so each group that had purchased Web of Science data kind of has their own version of it because of how they clean it and how what they do with the data. And then they, like I said, they didn't have the expertise. So we think this will solve those problems, and IMLS agreed with us and gave us a fairly large grant, one of their largest that they give. The team here is Ginny Wittenberg. She's our project director, and she's at Indiana University, and she's in the library there. Myself, Val Penchev, who you will hear from shortly, following me, who's our Director of IT at IUNI. Sharon Yan, he's one of our research scientists, also a co-project director, and Rob Van Rennes, who's with the Big Ten Academic Alliance. Also, all these people, Jamie is the leader of the project, and all of us are the co-project directors. We have a lot of partners. To make this happen was really phenomenal, because a big part of getting the grant was running around and getting everybody's buy-in, and there were quite a few people who were willing to help. The grant required a cost share, which means that we needed to raise just as much from other contributors as we were going to get from the grant. So what you see on the left are all the universities participating through the Big Academic Alliance, my affiliation, Health Partners. We also have from within IU contributions from the Pervasive Technology Institute, the Big Data Hubs, which are NSF funded, Microsoft Research, which you'll hear about in the tutorial, and Web of Science. And you'll hear from Tim Otto today. I don't know if you can see that the bottom of the slide is a grant number. Okay, so this is sort of a schematic that you'll be seeing throughout the day that shows you what our conceptualization was for the project. And one of the most important parts of it, even though it looks like a small part on the slide, is the research asset commons. That's where I'm using the here, research asset commons. And this is where we expect our researchers to come and share, be able to save their own work if they want to keep it private, or share with others, share algorithms, share results, share cleaning, share pipelines, and so on. So the purpose of today's workshop is really to introduce the science of science research community to CADRE, what it is, so they get familiar with it. We want to give you some examples from our fellows, we call them CADRE Fellows, which Sharon will talk about. We want their specific examples so you can see how this tool is being used and what it's good for. We want you to understand what the advantages of CADRE are, give you a little glimpse into the future potential for CADRE, and initiate a CADRE research community. So this is really a fundamental goal of our grant, is that we engage researchers. And I keep coming back to the Field of Dreams, if any of you know that movie from 1989 with Kevin Costner, where he built a baseball field because of basically voices that were talking to him, ghosts that said build a baseball field, and it had to do with his father and baseball history. But he built it and then they came. Okay, the baseball players came. Well, in our case, I don't think if we just build it, that's quite enough. We need to advertise it. We need to promote it. And we also need people to use it. We need the early adopters, because these are the people that will help tell us how to improve our platform, tell us what data sets that they need for the future. And all that feedback will help us make it a better product. We do have a sustainability plan going forward. So this initial piece that we're doing now, it's a 2-year grant. I think we'll probably be asking for a 3rd year of no cost extension. And then after that, we need libraries to subscribe to keep it going. But that subscription is a fraction of the cost of what it would cost to host it themselves individually. So the outcomes are, we hope you'll participate in today's tutorial. So this session will kind of give you the overview about CADRE and show you some examples of research. And then the next one immediately following in the same room will show you how to use it and help get you registered for the early adopters. We want people to use CADRE to give us feedback. And if you're a member of a library that's not in part of CADRE, to talk to them about joining. Okay, so our primary constituents are researchers. So academic research libraries, science of science researchers, students, library and information science researchers. We also have a level called secondary constituencies, which is public libraries. I mentioned there's going to be a free tier. It won't allow you to access the paid content, but will allow free content. There's teaching colleges, researchers in other areas, computer science, researchers who need to visualize large networks and research and development. Then we have tertiary constituents who'd be more our administrative users, bibliometric instructors, and the general public. In this tier, we've been surprised how much interest there is by, for example, university administrators who want to understand more about their own faculty by using this tool. So the overview is, I will give you the workshop purpose and goals, which I have done pretty much. The CADRE project, Val will tell you more details about it. Then we have Tim Otto here, who will talk about the Web of Science data, which is a big part of the platform. We will have our keynote from Claudia Borner, who will talk to us about the science of science and how CADRE can help advance the science of science. Sharon will tell us about the CADRE Fellows program, and each of our fellows we have more than 3 fellows, but the 3 of them will be 3 groups will be presenting today: Mike Park, Chow Min, and Sam Hansen. They'll give you the 3 applied projects that you can see, and then we'll have a little bit of question and answer and conclusion. So I'll leave you with this, that we're trying to develop a community of practice around CADRE. You can help us by getting on and using the platform, and then sharing what you're willing to through, whether it be, like I mentioned, data cleaning procedures and algorithms, analyses, results, pipelines, workflows, whatever it is that you're willing to share with others. And you'll see there's a marketplace where you can use what other people have developed. There's, we hope that eventually we will have standards developed by our community that will help the field move forward for replicability and many other reasons. But hope you'll give your feedback. What do you like about it? What do you not, or what do you, not that you don't like it, but what do you wish was there? What features would you like us to offer? And what data sets would you like? And please communicate with your librarian about these, because we have, as Val will mention, a product owners council, if you will, and that council makes decisions about what we end up having and not having. So in our platform, what we can do next, priorities. So that's how to get your voice heard. So with that, I think it's now Val and Jeff's turn. Thank you.
Hello, everybody. My name is Valentin Penchev. I go by Val, and I have a little overview of the CADRE project. We start with a dilemma that most libraries really struggle to present researchers with sustainable and standardized access to licensed and very complicated data sets. You would see in CADRE we explore both the open community data sets, which usually tend to be very large and complex for individual libraries to be able to adhere to, and also licensed data sets, which are usually cost prohibitive for libraries and small colleges as well. We also find, I'm not sure if you can see the bottom of the slide, we also find that a lot of researchers who need to use those data lack the general computer and programming skills to be able to embark on a journey of mining it themselves. That's why part of the CADRE is a graphical user interface that allows users to generate those queries for themselves. So what is the solution? We believe it is CADRE. This is the project that provides secure access to licensed and complex data sets. It also allows users and researchers to share not only the data, but their derived results, their algorithms, their queries, and the data sets that they work with each other. And it will feature a graphical user interface, it will feature data in a standardized format, and it will be an open platform for creation of new data standards. I want to pay a little homage to my home institution and give you a few words about the Indiana University Network Science Institute that I represent. The work here I present is not my own work. It's I'm part of a team that I had the privilege to lead. A few words about IUNI, as we call it. We are an interesting startup in a well-established higher educational institution. We're formed explicitly out of any schools, out of jurisdictions of deans. We don't issue degrees, we don't teach students. But we do work with more than, I believe, 150 faculty affiliates on campus. CADRE is one of our projects. We try to strengthen the theories of network science all over the world. And we engage in multiple other network science research, including brain connectomics, diffusion of information in social media, and so on. We have two teams. One is the IT team, which I lead, and I want to present here, who are the people driving the technology behind the CADRE project. And we also have a team of researchers. Shaoran and Felipe are representative of our research scientists, and you will see a lot of the CADRE Fellows coming in. So, what are the goals of the project? First, we want to gauge user needs and user expectations. One of the main criticisms any IT project gets is that it gets built without the gauging the needs of the researcher and user behind it. We're going the opposite approach through the user stories that Shaoran will mention, through other product council, and through communication workshops like this. We're trying to engage you, the audience, and the potential users to help us build the features that will work for you in the project. We have identified different communities and different research goals, starting with the informatics and computer researchers labs. These are usually people who by themselves know programming languages, know how to use databases, or in the case of some more established professors, have their own labs with PhD students and postdocs who know how to do this very well. What they ask us all the time is very simple. We need access to the raw data, we need the application programming interface, we need notebooks, and how much computer resources you can provide us. Then we have the science to science community, who are researchers in different fields, and we're trying to provide them access to databases. You will see as part of this project, we keep data in its raw format, and we also parse it in relational databases. We also parse it in graphical databases, and we try to find the hybrid solutions that work best for individual queries. For people with even lower computer skills, we try to offer a web interface, which is a query builder that not only helps the researchers create the right query for the job, but it's also trying to find and suggest the best technology from the underlying technology repositories that will be able to answer the query in the best possible manner. Some of the features, when you log on to CADRE, you start with the Research Asset Commons. This is a shared repository where you can control your teams, you can create your own projects, you can create your own packages and share data as well as derivatives and algorithms amongst your team members, with your entire university, or with the rest of the world. It's open for collaboration, as I mentioned, and it helps in reproducibility, replicability, assurance of provenance, and data guardianship. We give the ability to create publishable packages, which are based on DOIs assigned at every different permutation of data. So people can come and really not only retrace your steps to ensure the same results, but also use your data with their algorithms, use their data with your algorithms, keep building on the community edition of the project. As I mentioned, three different ways of accessing data. We have the raw data access, which comes in any format the data was given to us. This is usually XML, JSON, or CSV files. We have containerized packages that can work on the data, and Felipe and Matthew will be showing you a little bit of this. We also give access to data using some cloud-native technologies like uSQL and AWS's Athena and Glue dynamic schema technologies. I am, as I mentioned, the IT director. I'm the technical lead for the project. I lead the technical team. I would spare the technical details for the general audience, but I'm available here for the entire length of the conference. If anyone is interested in how exactly we do this on the back end, I would like to have some nerdier talk with you. Data access. Matthew here, our data manager, is engaged with the Research Data Center Technologies at Indiana University, a pack of database experts who are currently testing multiple databases in different realms of the field to make sure we have the best technology for each individual query in the project. Right now, we're testing Tiger Graph, Neo4j, Agents Graph, cloud-native technologies, and memory graph for the graphical aspect, and multiple relational databases. And finally, working on a hybrid solution of our own that will engage both technologies into making sure the queries are answered a little bit faster. When I say a little bit faster, we're able to achieve 10-fold increase of speed compared to the conventional relational database technologies. And the web interface, query builder with suggestion of the best database to be used on the backend, the base technology, and giving the user full automation and control if they want to do things manually as well. Here is the CADRE project that Matthew mentioned already. I have a few more details on it. It all starts with authentication, a federated technology, which goes directly to your university to check your credentials, if you are logging on from a university as well. There is a free tier, which includes Google login for now, and we're currently expanding to Facebook and Microsoft, which will allow this to be used by everyone in the world. But the federated technology also gauges what is the level of what is the access a particular person has to different data sets on the project. It all started, as you know, as a BTAA agreement with the Web of Science group. So if you log on from one of the Big 10 universities, you would have access to the Web of Science. If you don't, you have access only to the open sources, which are also in abundance. The Research Asset Commons I discussed, and from here one can go to the query web interface or to the multiple products that are currently being built. These are your generic Python notebooks that one can run their own code, or all the packages that we'll show you a bit in a minute, and we hope you as a community will continue to build as part of the project. The data itself, one more time, is kept in its raw format, and it's available for anyone to use their technical skills on. It's processed in, well, it is being processed in a multitude of databases, currently again relational and graph, and we hope down the line to be able to use local institution power to resolve some of those queries as well. This is coming in the future, not ready yet, but the idea of the CADRE project is through the federated logging system, if you log on from a university that has its own powerful infrastructure, supercomputers, data stores, and so on, they to be able to be utilized on premises as complement to our cloud system. This is all from me, and again, I hope I'm here to answer any more technical questions until the end of the conference. And now I want to welcome Tim Otto from the Web of Science group, who will give us some more. That's him.
Thanks, Sam. Bring up 10 slides.
No, sounds good. The ones in the email, those are perfect. Yep, that's fine.
Oh, that is it. Oh, yeah.
Okay. No problem. Hello, everybody. How are you doing? So my name is Tim Otto. I'm with Web of Science Group, and I'll be taking you through the Web of Science data aspect of CADRE today. How many people know what Web of Science is? All right, makes my job really easy. What you might not know, so we've changed our name a number of times over the last 2 years. We're now called Web of Science Group. We're still pretty much the same core group of products that everybody knows us for. But yeah, I mean, we're in the middle here. We support different funders, researchers, institutions, publishers, and in a kind of a different lens, you know, our core business is Web of Science, so it is the underlying data to everything, right? But we're supporting different workflows through workflow tools, analytics, and user researcher tools like EndNote as an example. So I'm not going to go through all of our brand names because that's really confusing. But the main point about this slide is really just that we have two constants in the entire research ecosystem and through these workflows. And those are the researcher, they're in every single aspect of it, and then the Web of Science data. You know, they touch both of them. And that's, you know, that's really the point, is that, you know, we're building a foundation, and what we build off of kind of like our integrity, and everything that we're doing is built off this data. So this goes back to kind of the core elements of what makes up the Web of Science core collection. You know, at the heart, it really is, it's a high quality collection of journals, books, and conference proceedings. We have a team of in-house experts that's curating this data set. You know, so it's going through an evaluation process to ensure that the journals, the books, and the proceedings that are being accessed are high quality and to high standards. So we have this whole evaluation criteria that goes in, a team of experts that's making decisions on which journals they see, you know, has quality but also has impact criteria. And then for those journals, which are in the core journals, we give them an impact factor. We also have a new addition called the Emergent Sources Citation Index, which is adding about 7,500 new journals to our collection that we added in the last couple of years. So to kind of break it down, you know, we have these two sections. We have these quality plus impact journals, and then we have this quality content for journals, but quality evaluation that goes through for books and for conference proceedings as well. And just to let you know what this evaluation criteria looks like, because it hasn't been transparent in the past, there's a whole a list of checks that our editors and our evaluators will actually go through in the whole submission process when a journal goes and they want to be indexed by the Web of Science. So I'm not going to go through every single one of these points. The point is that there is steps that are going through in each journal, no matter, you know, who they are, you know, as long as it's peer reviewed, it's got to go through all these steps and to ensure that it gets into the Web of Science. And then to kind of reinforce, you know, who we are within the scholarly, you know, ecosystem. You know, again, we've been here for you know, since the 1950s. We're not a commercial publisher, so we kind of sit in the middle, and we're publisher independent, which gives us a lot of flexibility into what we want to do, so we don't have to adhere to you know, think about, you know, certain business models or anything like that. We have no conflicts of interest, no professional commitments. The team that's doing these evaluations, they sit completely separate from, you know, from any of us. They have their own, you know, evaluation process that they have to adhere to. They can't sit on any editorial boards. They can't publish in any journals, and this all goes into, you know, what makes Web of Science objective. So some, and maybe even within this crowd, don't even know us for Web of Science; they just know us for ISSI. You know, we still get that as well. So 2 years ago, our new CEO, Annette Thomas, when she started, she said, you know, you guys have lost kind of your identity as being Thomson Reuters, and I want to reestablish ISSI, which is the Institute for Scientific Information. And what this is kind of our internal university or our internal R&D. team. It is a team. They are here. There's a lot of them here. They're floating around. We have Jonathan Adams is here. One of my colleagues from Rockwell, Joshua Schnell is here as well. But what they've done this year is they've started to put out these thought leadership pieces and start to do some evaluation and engage with the community that's out there. So they've done 4 reports this year. You can see them on the screen. One was about the Plan S footprint. Another one they just released was about a G20 scorecard. So, seeing how everybody's benchmarking in the G20 in their research performance. So they're doing this, just as, something to do. And they also challenge us internally about what's good and what's bad. So they kind of are our internal voice about what we should be doing, how we should be implementing products. Is this responsible metrics? Is it not? That's what this team is about. So, and that kind of builds on to what the Web of Science group is. So kind of turning to the data source now. So we had the privilege to be one of the first data sets on the CADRE platform and work with the Big Ten, and I've worked with the Big Ten for many years, so it was a nice relationship that we have with the Big Ten. But what makes kind of the Web of Science metadata unique, again, it's built on this foundation of high quality, consistency, and trust. So we have over almost 21,000 journals now, peer-reviewed journals that make up the Web of Science core collection, over 100,000 books, number of conferences. We have a massive citation network out there, 1.7 billion cited references. And it's also the historical piece too. So, if you're doing bibliometrics and you need to go back in time, Web of Science is pretty much, the most reliable source that's out there that you can go back in time. The other core pieces that we have is address information. So we're doing some unification, organizational standards to make it easy to search on institutions, identify researchers to their institution. And the other thing that we focus on is also the funding acknowledgement piece, and starting to include funding acknowledgement data into the data set, so you're able to track, where the funding is coming from and the outputs that are coming from that funding. So the last piece this is a little bit of an old slide, but the idea here is that we've done analysis even using our own data sets, so going into Web of Science, creating a comprehensive search and understanding who's actually publishing using Web of Science data. And then you can see, a number of different disciplines, over 200 disciplines that are beyond the traditional bibliometrics. And, there's a lot of good examples that come out of Indiana about, that are not traditional bibliometrics, which I think shows the range of the data set, shows the uniqueness of the researchers that are out there, and being able to use data that they can get access now to and come up with some really interesting projects. So the last thing I'll just talk about is the value of good data. So these are actually customer comments that we've had, just from researchers that have used our data. It's data quality is I'd say one of the bigger barriers to adoption for sure, especially in machine learning and in certain techniques. So, the combination of having good data with a platform that's usable, and then you can access these different tools and manipulate the data, is going to get you, to the results a lot faster. And that's the concept that we're trying to bring together with, the Web of Science, the data quality that you get there, and then this amazing platform that's going to also bring additional data sets onto the platform as well. And so I'll leave you with our updated marketing tagline, which is better data, better decisions, better outcomes. And that's it. Thanks.
Very much, Tim. Now it's our pleasure to welcome Connie Warner, our keynote speaker for today. We'll talk to you about science of science and CADRE. Put that down. I can minimize that.
how many of you have access to Web of Science, the raw data? All right, so half of you. That's good. Congratulations.
Hello. I didn't know
It takes big endowment or some big startup funds to actually get to the. Obviously, as soon as you have access, you can attract a lot of good postdocs. You can attract good faculty. You can attract good funding. You can write technology papers. And if you then find ways to use that data, the spending data, the second data, the social media data, you're golden.
Thank you, Carl.
You have to work 15 minutes. So it's an absolute pleasure to be here. When I started in this field about 20 years ago, it was very much a cottage industry. There were many teams which, for whatever reasons, had managed to gain access to either Scopus or Web of Science data, typically not both. And they also found the resources to have $100,000 or $200,000 a year to just take good care of that data. That's a huge burden for one faculty member. Typically, one faculty member cannot sustain something like this for 10 years, 20 years, or in some cases, people do 50-year careers today. So how do you go about it? And I have a bunch of slides here, but I might deviate from them. But if you want them, they're on the Twitter feed. So just go to KDCNS and you can download them there. And in the meantime, just to re-emphasize what you just heard, there are 150 faculty members at Indiana University which study science and other networks by scientific means. IUNI, the Network Science Institute, came into existence because we are so many that are interested in analyzing, visualizing, and modeling networks. And it's wonderful to have that team because it brings production strength software development and data curation to these 150 faculty members and their postdocs, their PhD students, and the many classes they are teaching. So, talking about big data, back in 2009, some of you might have used the scholarly database. So that was our response to seeing that cottage industry of many little teeny tiny teams, which had 5 to 10 people in each, and trying to do science of science studies in a reproducible way. As you know, many of these teams have cleaned the data further, they have interlinked that data, and they did it all in different ways, meaning they could not reproduce across the institutional boundaries. They could also not share these data sets. There are a number of events which tried to at least share the cleaning algorithms and processes and methods, so that whatever CWTS has figured out, Vincent Zarigui could use in Montreal. And whatever Vincent had figured out, we could use at Indiana University. And that was that, and it was hard still. And again, the scholarly database back then cost about $100,000 each year to sustain, which had to come from external grant funding. And as you see, it had some of the data sets we're talking about today. It also had some of the patent and funding data. Now in 2019, we have much more data. Also news data, social media data, IoT data, which is of interest. I'm very proud to tell you that Santo Fortunato and Vai Ahn, they're on 2 teams which currently got funded out of Minerva. These are 5-year center-level grants which basically support science of science research. So this is also going to use this CADRE infrastructure, but it also brings additional research dollars to Indiana University for this kind of research. You might also know that Filippo Metzner got a major center grant for fake news. So there are 3 center-like grants now at Indiana University. And I think here at ISSI we have the 5 of us in the room, and then we have 2 students from IU, and of course also Cassidy Sukimoto, which is currently the ISSI president. So you have 8 of us here, so feel free to talk with any of us. As I mentioned, there were a number of workshops, and all these slides are available online. In 2016, James Springler and Evan Dude from the University of Chicago, we all together hosted a workshop that brought together researchers which wanted to use Web of Science as a research data set.
And as you see, many of the people you have here also presented there, and they mostly focused on research.
So if this is technical for you and you want to just see what kind of research can be done with it, please go back in time. I think it's still all very relevant to the discussions we have here.
Some of you might have made it to China to the last
ISSI conference. We had 2 events there. One was an
tutorial workshop
on reproducible research.
It is really not science if you cannot reproduce. And so this CADRE infrastructure, for me, I think provides the first time a serious approach that the many teams which now have access to the Web of Science can reproduce each other's work. This is not possible right now, but I think it will be with CADRE. And as you see, this is a very international team, which is all very interested to facilitate that. We also had a poster there, and as you see here, the originally implemented IUNI data enclave. And some of the parcels that were originally used to take the raw ISSI data or the raw Web of Science data and then pass it into a database, they are on GitHub, so you're very welcome to try those out. Now, Pinchip already showed you this overview of the many different technologies which have to come together. And again, typically this is too much for one faculty member to sustain over many, many years. And so I'm just absolutely glad that the IUNI team got the funding and stepped up to the challenge to really make a serious infrastructure for science of science research. So what kind of research would I do with it? Well, you might be familiar with the exhibit. So we now have 100 maps of science, including some of the first ones by Kevin Boyack and Peter Clavens, which I think you will also see here.
You have maps of Wikipedia data, you have maps of grant funding data, you have maps of collaborations using Scopus data, you have maps of science fiction
books and other novels, and it's very much like Amazon. If you like one of the books listed here, you might like the ones close by. And you can zoom into those maps online. And recently we added interactive data visualizations, which we call macroscopes. And we now have 20 of these, and they will actually come on display at the next CallNet in ISSI, and also there will be a soft release at the IEEE InfoVis conference in Vancouver. So if you're interested to explore interactive data visualizations, go online and just check them out. You have mega regions which show how people travel to work and back to home every day and how that actually changes the geography of the US. You have smelly maps which are based on Twitter data, showing you where the good and bad smelling areas of the town are. This is London for your information. And there are some zoo areas which are in yellow here. There are some nice green areas of parks. And then there are the high emission areas, the streets across the River Thames. You have news data also, and again, these are interactive maps. And as you might also know, recently we have been starting to do more models of science. So we had a number of events that brought together those which are not just interested to visualize old patterns in data sets, but also are interested in computational predictive models of science. Many of these reports are also online. We had a Sackler colloquium on that topic, which looked at the rankings and efficiency of institutions and what kind of computational predictive models exist there. We looked at models that try to predict what might happen to the higher education bubble. It's critical to get workforce training, but also training in general, right? Innovation diffusion and technology adoption, but also infrastructure and standard setting needs. All these presentations, which happened at the Beckman Center, are available online at the Sackler YouTube channel. And there's now also a special issue of the Proceedings of the National Academy of Science. So you're welcome to look at it. And this also can be held up to say, here, we can, in a reproducible way, not only analyze science and education and technology and innovation, no, we can predict to a certain degree with confidence intervals what might happen if you make a certain policy decision, if you give a certain amount of money to a certain team, etc. So I would help you all, I would like to help you all understand that it's not just analysis of old data, getting age indices and getting all kinds of other indexes out of that data, but also trying to help those which need to make decisions on where to invest money, personnel, compassion, that there are predictive models that can now be applied. At Indiana University, we also started to prototype what we call science forecasts. So here you have a moderator, the lady in red, in front of a large wall that shows developments in science, technology, education, innovation. And she is explaining to you what might actually likely happen in certain areas of science. And there's a YouTube video on this. So again, download the slides and look at it. It's a 5-minute video. I can't fit that in here. So check out the papers that came out in that special issue. I have a few of the copies here. And ultimately, in my work right now, we are about to get funding to more systematically study the interplay between job market demands, what's taught in universities, but also in workforce training and in online MOOCs, and what is happening in the science technology landscape. So you have papers patents at the lower level, an entire landscape full of it. You have all the courses that are taught around the world, and you have job market information. How do those three levels interact with each other? What kind of delays exist? So if you're interested in that, let me know. And I won't have time to go into this. But there is a huge demand for this kind of information, especially given the rise of artificial intelligence. Many, many people have to be retrained. And of course, our children, I have 2 teenagers, I need to advise them what they should learn today so that they are having a job tomorrow. That's non-trivial. So I will make it through this. But again, get the slides. Watch out for the next atlas. It's actually the Atlas of Forecasts, and it's going to be out for Christmas 2020. So if you still need a present for next year, that's your Christmas present if you like. Thank you all.
Thank you, Connie. So much. A real thrill to have that overview of science of science. Where do you get so much, I don't know, real estate per slide? I don't know what to call it, but Connie, as always, a crowd pleaser. Our next up is going to be Sharon to present his slides. I can get them up. So Sharon. About the CADRE Fellows.
Yep.
Okay, thanks.
Good afternoon, everybody. So as previous speakers have always repeatedly emphasized, a key goal of this CADRE project is really to bring the research community together, to work with us so that the infrastructure we build will actually serve real users of data. And that's why CADRE Fellows, we started this CADRE Fellow program. So just give you a little bit of background. Many of them are here today. So each team, the first round of fellows, we have 7 teams. Each one of them has a representative here at ISSI. And we have to thank Web of Science for sponsoring their travels. And so everything started, this fellow program, back in the April. That's when we announced it. And so things are just getting started. So we are trying to work with them, and their user experience is very important in how we design the platform. And so at this event, the IC workshop and the tutorial to follow, we really sort of try to setting the stage for our long-term collaboration. And so there's a few more events that's coming down the line next year. I'm pretty sure our collaboration can last last even beyond that end of the project. We hope for really, a continued collaboration. So what do you get at the CADRE Fellow? So by the way, the CADRE Fellow program is still open, technically speaking, and as our team grows, currently we are sort of saturated in the because our team still focused on developing the platform. In the future, we have more resources. We plan to expand the program, so that's why I've kept the program open. If you're interested, you can always go back to our website. I guess since previous we haven't mentioned it, I should give you a little bit of glimpse of our current website. So it's very easy. If you go to the URL called cadre.edu, this is our newly launched website just a couple of weeks ago. And if you get to work with us, you can find information about details of how to apply for a fellowship status, and all you have to do is to fill out the proposal form, which the fellow teams here has already done. So I'm not going to details. I'll just leave it there. By the way, you can get detailed information of this events, the workshop and tutorial here as well, just by going to the news and events. And the workshop is right here. And we do plan, so right now we haven't provided slides, so as Kadi has suggested, we plan to make all slides open and you can find them afterwards as we collect them in this website. And we're also recording the event, so you could also expect a video recording. So let me try to go back. Oops, wrong one. Oh, it's the correct one. So I'll just quickly go over some of the fellows who unfortunately didn't get the opportunity to present here today. We're hoping to really work with them in the future, in our future events. You can hear more from them. I think for this group coming from Purdue University, I think Michael Witt is here personally. They plan to connect the cryptographic metadata set with actual research data, which is data citation, to study how real research data play in the larger scope of science to science. In this case, in particular, in STEM education research. So this is a group from Michigan State University. I think Scout is here. Yeah. So they're focused on studying, I think, Sustained Development Goal initiative by the United Nations and how these initiatives has led to research collaborations around the world and evaluate their effectiveness. So if you're interested in these different topics, feel free to speak with the fellows here at ISSI. So this is a little bit shameless self promotion because I'm a co-author of this, collaborator of this project. So Adam Lizzie is also here. I think we have you have a presentation which day? Tomorrow, right? At the main conference. On Thursday, okay, yeah. So check it out, and we do plan to expand our geolocated analysis to a bigger data set, and CADRE platform will be very important in terms of data. So the next three fellow teams will actually have a presentation right after me. So I'll leave the details to them, and I think the first presenter is Michael Park from Minnesota. And I think I have to switch to his slides here. It's not here.
That's it.
This one. Okay.
That's one of them.
Okay.
Point if you need it.
Okay. Hi, everyone. I'm Mike. I'm a PhD student at the Business School at University of Minnesota. Before I get started, I just wanted to thank the CADRE team for putting together this awesome project and also giving me the opportunity to come out here and present my research. I really thank you guys. So the title of my presentation is Changing Characteristics of Innovation. So I'm presenting this on behalf of my team. We're all across University of Minnesota, University of Arizona, NYU, Carnegie Mellon. So the roadmap for my presentation is as follows. So I'll first introduce the motivation behind my research question. Then I'll introduce the research question. Then I'll briefly talk about a thing called the CD index. It's a bibliometric measure that the PI of our team, Russ Funk, who's also my advisor, came up with. It's a central part of the way in which we're addressing the research question. So I'll briefly talk about that. And we've only really delved into the Web of Science data for the last few weeks, so we don't have much results, but we do have some preliminary results that we are really excited about. So it's a very early stage project, so we're really open to any and all feedback. We'd actually really appreciate any ideas you have after you see the preliminary results. So I'll give you those. And then we'll briefly talk about CADRE, and I think we're actually doing questions and answers at the after all the presentations. So we'll hold off on that for now. So first, the motivation. So I think a lot of science of science research has found so far that it's becoming increasingly harder to do any sort of innovation, including scientific research. So that's been a common claim, general claim that's been made by the science of science literature. And that's not a controversial claim in and of itself, we don't think. But when you try to reconcile this claim with some of the empirical data, I think there's some interesting questions that arise. So for example, this is a graph showing the number of papers published in the Web of Science archive over the years. So the top orange line shows the number of papers across all editions. The green line, the second bluish green line shows the number of papers across the science papers. The purple line, the social science papers, and the bottom green line, humanities papers. Now, obviously, Web of Science is science heavy, but the main point here is that there's been this crazy exponential growth in the number of papers published, at least according to Web of Science. And if the claim is that scientific research is becoming harder and harder to do, intuitively, this doesn't really sit completely well with that claim, right? So we think maybe to better understand how innovation or science is changing over time, it's not the question of is it getting harder over time, maybe a little bit too much. Maybe we need to step back and think about a little bit more of a nuanced question to understand what's happening over time with science. So we think maybe a more appropriate question might be, is innovation changing in nature over time? So we think that's a more subtle question that could potentially help us better understand what's exactly happening with science over time. So the approach we've taken to kind of answer this question is the CD index. So as mentioned, it's a bibliometric measure that distinguishes between two different types of innovations. So on the one hand, you can have a consolidating innovation. So let's say a new paper does an empirical test of a theory that already exists. So it's building on something that already exists. It's kind of enhancing something that we already know. So that could be considered more of a consolidating innovation. On the other hand, we can have a destabilizing innovation, which is something more radical and potentially displaces something that already exists. So maybe someone comes out with a new theory that completely displaces an existing theory by better predicting a certain empirical phenomenon. Right, so that would be more of a destabilizing innovation. So I don't think I have time to go into the details, but the way the CD index measured this is by looking at the patterns of forward and backward citations of the focal paper. Okay, so it ranges from -1 to +1, and if the CD index falls between -1 and 0, it's considered a consolidating innovation. If the CD index falls between 0 and +1, then it's considered a destabilizing innovation. And the closer to -1 it is, the more consolidating it is. The closer to +1 it is, the more destabilizing it is. Okay, so this is a tool that we're using to try to better understand what's happening with science of science over time. And it's originally developed within the context of patents by Russ, but it's been applied in some recent Nature and Science papers dealing with science of science. So we're also trying to make that application to better understand what's happening with science of science over time. So let's actually look at some data. So this is the average CD index of papers over the years, science, social science, and humanities. And as you can see, the common trend here is that across all the fields, the CD index seems to be approaching 0. Okay, so what that means is, according to the CD index, papers on average are becoming neither too consolidating nor too destabilizing. So we think this is really interesting, but as we mentioned, we're in very early stages, so we're still trying to figure out why this is happening. And one of the hunches we had, one of the leads that we're chasing is maybe this has something to do with that crazy exponential growth in the number of papers that are coming out. So we're considering different measures, different mechanisms to look at. And two of the measures that we've been looking at are these. So on the left, we have unique to total articles cited each year on average by papers in science, social science, and humanities. On the right, we have unique to total words and titles of articles, science, social science, and humanities. And you can kind of interpret these two measures in a related way. So first, the unique to total articles cited. So you can think about this as, papers that researchers actually read, consume, and decide to cite in their papers out of all the papers that exist in the world, okay? And on the right, if you kind of make the assumption that words roughly map onto ideas and concepts that are out there, okay? So that means that this is measuring the ideas and concepts that researchers are actually using in their papers in proportion to all the ideas and concepts that are out there. Okay, so one kind of interpretation of all these graphs that I've been showing you that we've kind of been chasing is, in response to this exponential growth in the body of literature of science, researchers haven't been able to, no one has the capacity to digest all this information that's being produced. So what they end up doing is they end up focusing on a narrower set of science to conduct research in. And somehow this is leading to research that tends to be neither destabilizing nor consolidating. So this is one conjecture we have that we're still trying to figure out. If you have any ideas that might better illuminate what we're seeing here, we're very happy to hear about that. So finally, just how CADRE is going to be a very central piece of this project moving forward. As you heard from the previous CADRE members, Web of Science data can be really huge, and kind of, especially the XML file can be very hard to deal with at times. But CADRE's initiative to provide convenient access to this is really helpful for us. And also, we would like to contribute to CADRE's initiatives as well, mostly through the Research Asset Commons. So Tom, who's at University of Minnesota on our team, is working on an unsupervised author disambiguation algorithm that we're still trying to fine tune and hopefully share on the Research Asset Commons very soon. And Russ is trying to create a more efficient CD index script that he also hopes to very soon share on the Research Asset Commons. We're also very excited about some of the textual data that's coming out of the Microsoft Academic Graph feature, which hopefully will have the abstracts and titles, and we have some NLP ideas that might really push this paper forward as well. So I think that's all I had for you guys today. Thank you.
Well, that's really exciting. And as Michael has mentioned, that the research ISSI really needs contributions like that and in our tutorial. So if you're interested, stay for our second session. We will demonstrate a preliminary implementation of that and how you can share your algorithm and derived data in a reproducible way. So I think we're leaving the question to the end. Okay. So I think the next presenter from our fellow team is Charming. Let me try to find his slides here. Oh, is it updated version or not? Okay.
Good afternoon, everyone. I'm Chaoming from Nanjing University, China. It is my honor to be here to present our study supported by CADRE. And the work is a joint work by my collaborators and I from Nanjing University and Indiana University. So this talk is about the identification of citation patterns of scientific breakthroughs. We know scientific breakthroughs, the ones, the frontiers of science, but the quantification of scientific breakthroughs is a tough task. Previously, we used external bibliometrics. Bibliometric indicators such as the number of citations, the number of references, the size of team of the author team. But these indicators only have weak discriminative power. In this study, we introduce the perspective of the dynamic citation process, which I will explain later. And the next question is, which work can be recognized as scientific breakthroughs? In practice, we choose works recognized by professional institutions such as Nobel Prize communities. So they are considered breakthroughs in science. And then we compare Nobel papers with their non-Nobel papers. So we investigate the citation patterns of the two groups of papers in two dimensions. The first dimension is temporal citation pattern. In this picture, we can see the x-axis is the publication time, and the y-axis is the number of citations after publication, a paper's publication. So after a paper's publication, it will undergo many stages. Including it will receive the first citation, and then the citation will take off to a relatively higher level, such as the first citation peak, and then maybe citation summit, and so on. This can be quantified. And in the second dimension is the structural citation dimension. In this figure, we can see after a paper's publication, it will be cited by following works. This is the works are called the first generation citation, and then these works can be cited by their following works, and their following works are called the second citation generation of the source work. So we can there will be citing networks of those citation generations. In this study, we collected data for 4 generations of citations to the works under study, and the data are within 4 years of initial publication, because we want to identify if there is difference between the citation group, between the two groups in their early, just after early publication. And the Structural metrics are common metrics of networks, such as average clustering coefficient, network density, and connectivity. As both temporal and structural dimension requires access to complete the citation database, we are very lucky to be supported by CADRE. And CADRE provides benefits such as access to datasets like Web of Science and Microsoft Academic Graph, and computational resources that can handle the big bibliometric datasets, and associated analytics tools and storage. In addition, we can also communicate with our CADRE Fellows and our technical team through various communication channels such as email, Slack channels, and GitHub repositories. Besides the raw data, we can also share with each other derived data algorithms, methods, and the data flow. So next, how did we choose the data? Following a work by Shen and Bravasi in 2014, we selected 116 public papers that helped the authors won Nobel Prize, and construct a control group where each paper has the same publication year, value, and roughly equal citation impact with a counterpart paper in the Nobel group. Then we compare the citation patterns of two groups. So in total, more than 90 million citation pairs were extracted from Web of Science database. First, let's see the performance of Nobel Prize. The Nobel Prize papers received a citation shortly after publication, but a small proportion of those papers remained uncited until 3 to 9 years later. And to our surprise, a significant number of papers took off 5 years after publication. Some even took off about 25 to 45 years later. With such a long preparation period before takeoff, several papers accumulated more than 100 citations, but most obtained fewer than 100. We also find that there is a long time span between publication and the citation submit. This suggests that Nobel Prize papers has a long period of citation groups. As statistics show that typical papers reach their citation summit 2 to 6 years after publication. But our data show that for Nobel Prize papers is a little bit different, as for most of those Nobel Prize papers, the summit comes after the 6-year mark. With some more than 30 years. This is the table 1 shows the temporal comparison between the two groups, and table 1 shows the temporal dimension. We can see that most indicators can differentiate the two groups, but TOS, which stands for takeoff span, and TOS, TOC, which stands for takeoff citations. These two indicators can are obviously different in the two groups. This is the temporal dimension. On the other hand, in the structural dimension, we find the difference between the two groups are even more significant, as average clustering coefficient and the connectivity of the citing networks, especially in the first generation and the second generation, can significantly distinguish the two groups. More specifically, we find that Nobel Prize papers took off 4 years later than non-Nobel Prize papers on average, and they had far more accumulated citations, nearly 2.5 times at takeoff. And Nobel Prize papers have higher average clustering coefficient and greater connectivity. This implies that there are more interlocked structures exist in their direct or indirect citing networks. This suggests that scientific works with significant novelty can inspire subsequent works that are also relevant to each other. To conclude, most citation measures can distinguish novel papers from non-novel papers, but three measures, citation takeoff, average clustering coefficient, and the connectivity, do significantly separate the two groups. Although scientific, so we can conclude that we come to a conclusion that although scientific breakthrough is not easy to quantify, it may have left visible marks in the process of citation diffusion. And these marks provide potential traces for identifying innovative scientific works at an early stage. Our results show that works with sufficient scientific novelty reveal unusual characteristics in the first one or two generations of citing structures shortly after publication. In subsequent research, we hope to, with the help of CADRE, to further excavate the potential of citation diffusion characteristics in identifying early innovative scientific works. That's the end of my talk. Thank you.
Great work indeed. That's really intuitive and revealing how Nobel meaning papers are different. And by the way, his Chongmin's collaborator Yibu will also be giving a little more detail on the technical challenges they faced when they conduct this research, especially when building these high orders of cascades of citations, which has always been a challenge. And so stay for the tutorial. Next up, I think it's Sam Hansen from University of Michigan. Let me try to switch to zero slides. More. Oh, this one. Got it.
Hello, y'all. Bring up this presentation. There we go. So I think I have a weird little special thing about me. I am, I believe, the only person involved in two CADRE Fellows. Yeah, well, I have to. I'm going to talk about both of them shortly here. This is going to be both about mathematical biology as well as systematic mathematical research analysis. So the first CADRE Fellows group that I'm part of is this one, along with Marisa Conte, Scott Martin, and Santiago Schnell at the University of Michigan. We are trying to compare legacy and emerging journals in mathematical biology. And so the goals for this project, which I'm just going to touch on because this is the one that we are a lot less forward on than I am on the other project. And this is, we're going to develop and test methods for comparative bibliometric analysis and content analyses. We're going to hope to provide insight into publication trends in theoretical and applied domains, specifically within mathematical biology, but we hope that it will be able to be abstracted out beyond that. Santiago is specifically an editor of mathematical biology journals, and this project came out of some work or some analyses that they were doing when they were looking at publication trends in their own journals. And that's to help editors distinguish between their journals in this field. And we also want to give authors new factors to consider when they determine where to publish their work, because these mathematical biology journals do have very specific things that they're supposed to be focused on. But over time, especially with some of the new emerging journals, people have been publishing very specific journals outside, or specific articles in journals that don't actually focus on that when there are existing journals that do. So the other project, this one I'm involved in with nobody, is a systematic overtime analysis, similarities and differences in research across mathematics and the sciences. So I'm a mathematical chauvinist, I think would be the correct way of saying it. I love mathematics, and I wanted to look a lot at, scientometrics of mathematics, but it doesn't seem like too many people focus directly on math. Which is something I decided I would really like to, because as I said, mathematical chauvinist. So I'm trying to develop a holistic understanding of mathematical research using, they're primarily bibliometric, but also some scientometric methods. compare mathematical research to research across other STEM fields. This is the big part of it, mostly because I don't believe that science and other STEM fields should actually be lumped together in analyses, because their behavior is rather fundamentally different in research. And I also want to help mathematicians understand how mathematics has grown over time. I've done a lot of work with mathematicians over the years, and I want to give something back to them. So as far as why CADRE, it's really the access to the two large bibliometric data sets, and hopefully the ability to link them together at some point, as well as the ability to analyze over large timescales and large subject groupings. So, you know, 1900 to 2017, all of mathematics, all of physics, all of computer science. Not really possible before having access to these large data sets. Also support for the technical and computational aspects, and community of practice. I've been saying back there with some other fellows already today. So I'm going to go through some preliminary results of the mathematical one. So here's a graph of all the mathematics publications as put up by the Web of Science categories. So the blue line, the line on top, that's everything that's classified under mathematics. And then you have the split between pure mathematics, which is the orange line. The green line is applied mathematics, and then the red is interdisciplinary applications. So you can see applied mathematics caught up in the late 90s and has since started publishing more than pure mathematics has. So here are some median reference ages starting in 1900, going all the way out to 2017. It gets really noisy in the early years because there's just not as many points of data. So it's going to be a little bit messier there. There are a few interesting things I can talk about to people afterwards, which is why we see this lowering down. I actually think I've identified why that happens. But most importantly here, especially if you think of how other sciences work, look at the current median reference age for mathematics. For pure mathematics is around 14 years. So half of things being cited or referenced in mathematics are now over 14 years in a just average paper. Now, if we look at, so this is the percentage of citations that are over 20 years old. So if you look down at, say, the 1980s, nearly 30%, or just over 30% of citations are coming from 2000 or sooner. If you go back further than that, if you notice there's a big difference between interdisciplinary applications and pure and applied math. Applied math, even though it has the word applied in it, tends to actually be much more theoretical than you would think. And so if you notice, those are a lot higher. Nearly 80% of papers from the 1940s have, or nearly 80% of their citations are from more than 20 years old. And that ties in with my favorite of these graphs. I love this graph so much. So this is the median oldest citation per publication. So I just took every single publication that has ever been cited in Web of Science. I clumped them by years, and I looked at the oldest citations for every single one. So if you look at the year 1900, the median oldest citation is around 110 years, which means that half of the papers that have been cited in mathematics in Web of Science from the year 1900 have been cited in the last 10 years. Mathematics does not age. It seems to stay forever young. And so I can show how that sort of ties together here a little bit if we go, let's go back. So if we look in here, the brown line, the one that goes all weird spiky and doesn't exist until the 1950s, that's computer science, because computer science did not exist until the 1950s. And the purple line is physics. Notice computer science was below mathematics at one point, and then come around 1990. There was a rather big spike in publications there. So let's look at some median reference ages. So physics is today around 7, which is half of the age of pure mathematics. Computer science is even newer. And interdisciplinary applications now sticks right there in the middle. But here is the big difference. So percentage citations over 20 years. I had to start this at 1950 because once again, computer science was birthed whole cloth apparently then 12 years after Turing published the paper. Not angry with Web of Science at all about that. So 15% of publication, or 15% of the citations for physics in 1950 are more than 20 years old. 70% of mathematics, 15% versus 70. Like, these are very fundamentally different disciplines. And this one, so once again, it's 1950, but if you actually extend this all the way out to 1900, physics existed back then. I did want to make one comment about this one first. Notice there is a massive spike in computer science around 1956 or so, where it goes all the way up. I identified exactly why this happened. There were the three most cited papers in computer science in 1956 were written by Shannon, Chomsky, and Kolmogorov. There were not that many papers published. Those sorts of papers are going to keep on getting cited for quite a while. The years after that, it's the next year, I think, is Arthur Samuel, which is what's causing that big spike up. So those are actually pretty easy to identify what's causing it. But as I was going to say, if you extend this all the way back to 1900, that physics line around 30, actually stays almost exactly straight, whereas mathematics keeps on going up. So the physics does not age in the way that mathematics does, neither does computer science. I know I'm making the same point around 10 times, but these are all different ways of measuring, and I think more pieces of evidence that talking about mathematics and other STEM fields in the same way might not be the most sensible way of going about things. And so this is some other research. I'm actually presenting a poster about this tomorrow. So if you don't know, sleeping beauties are papers that do not get cited for a while or have minimal numbers of citations, then all of a sudden have a massive spike. So I was looking at what the rates for these within mathematics. And so I'm using Key et al.'s sleeping beauty coefficient or beauty coefficient measure, where they looked at 1900 to 2014 in Web of Science. And then they just said the 0.1%, so just 0.1% with the highest beauty coefficients, we're going to define our cutoff there. And so you would expect for any field, if everything was distributed randomly, that 0.1% of any field's papers should be identified as sleeping beauties. With that being said, that would mean that a general mathematics paper has about a 4 times better chance of being sleeping beauties due to the way that mathematicians do their research and cite their research. And so, I mean, that's interesting, but what would you think would happen if we decide to look at highly cited mathematical papers with a, say, random cutoff of mathematical papers that get 800 citations? So we're looking at 740,000 papers here, so 1.3 million if you're looking at all of the different fields. Well, mathematicians don't get the 100 citations very often. 700,000 dropped down to 6,400, but 14% of mathematical papers with over 100 citations are classified as sleeping beauties. This is a tremendously huge amount of sleeping beauties. 0.1% jumps to 14%. And if you look at just the total across, it's still 8.5, even lumping in applied and interdisciplinary applications. So we are looking at very fundamentally different sort of citation metric or citation behavior. And this does come down to, if you think about how mathematics works, once a theorem is proven, it's proved. So there's no worries about citing something that's 30 years old that it might be out of date. If that theorem was true 30 years ago, it's still true today. If it was true back when the Babylonians did it, and then the Greeks did it again, and then the, I mean, probably the Italians did it again right around the time of Fibonacci. That's about how everything worked there. And then the Middle East was way ahead of everybody. And then all of a sudden we get to today. Those things are still true. I actually do know somebody who cited Euclid in a research paper in a research context 2 years ago. I believe that would be a citation age of 3,500 years, which I don't think we're going to see in theoretical physics anytime soon. So I think that, and this was one I identified in this analysis. This is, to date, the paper with the 3rd highest ever known beauty coefficient. It just so happened to have an awakening time of the year that he and all of these co-authors published their papers, so they just would not have seen it yet. But if you notice, you have that. It was published in 1969, almost no citations till would be around 2005, and then a massive spike starting around 2014. Okay, that is all for me. Thank you very much.
very entertaining and passionate presentation. You should keep going because we are ahead of time, I think. I guess that's usually the time for if we have any questions for all fellows, and you can go ahead. Yeah. Why don't you all come here? We have multiple seats here. Let's form a little panel here. It's even shorter than that because we started collaborating with them like just a couple months ago.
I started in January. Remember,
I
rebuilt your database before CADRE.
In 5 years. Wow. Not just about people already have that.
Any takers?
Yeah. We can only have 2 mics on at a time. So I have very strong feelings about this. Sorry, Tim. I'm a librarian at the University of Michigan. I have needs. I don't want them to serve. I want things like CADRE to do it. I have no interest whatsoever in burying more and more of our services and all of this data into things that we're going to have to pay money for. I'm very happy that we are paying Clarivate for this data because we would never have been able to build that data out on our own. And that's an incredible service that they are providing. I don't want them also providing the services that will allow me to query this data because that's just more money that we're going to have to do. I'm lucky that I come from a university that has a very large budget. And so we can keep on affording these things. But if we keep on tying more and more of our services into these companies, we're going to keep on separating the classes of the types of researchers that we have, and we cannot afford to be doing.
That's okay. They currently have some absolutely. So I think that
So I agree, and I know that everything is still going to cost money. But I do think that these consortial efforts, these getting together larger universities, where the larger universities that have more money can put in more money, and then those services don't get locked down. The thing that I'm worried about, and maybe Clarivate would end up being a good actor in this, I like them more than some of the other data analytics companies that are in the same space, who will go completely unnamed, but everyone knows exactly the company I'm talking about. And you know that if they were going to develop something and say they mentioned it's a drug company and give them a bunch of money, it's not like they wouldn't turn around and charge all of us a ton of money for the exact same service because they would have already built it, and that's an easy to capitalize on thing. Don't need to get into Marxist theory on all of this, but capital will keep on trying to create more capital. It's how the system functions. And so taking it outside of that system to universities, to places that are meant to exist to serve public good, and trying to put the services in their hands, I think is the way to move forward in a sustainable way, so that people in universities that aren't a part of the Big Ten or aren't, a large private one like Harvard or you have Oxbridge over in England that have money, so that they can still have access, that the growing and emerging world could have access to data and services. And I think that leaving it in the hands of capital producing companies is not the way that we can have that be sustainable.
Just answer a bit on the front of that. Having a great theory doesn't mean that this is a problem. What are we in charge here? We want other people proprietary data. This will allow us to have a platform that's better independent and possible. Because Harvard will be here, Microsoft will be there, other vendors are welcome. To answer the question about the drug companies, I think that we're not there yet. And we have a vertical markets that until you answer to medical needs, drug companies, more technical.
I would also draw my 2 cents. Here is to remind me this sort of very intense debate between the open source community versus the packaged software, and it seems that we've changed for good in recent years. The discussion with Apache open source license, which is I guess more common, and we are seeing a lot of industry players like Google and Microsoft contributing to this, so it's become kind of mutual beneficial ecosystem, and we're really hoping we can foster CADRE in a similar trajectory. So by the way, we will explain, but I just want to say everything we get from CADRE will be open source. We will share our source code and our data when the problem is ready. So that's our pledge, and I think that's sort of very much in line with Samuel's concern. I think that's also a big motivation of CADRE platform to democratize large data analytics for smaller institutions and just lower the barrier in terms of cost and technology. Tim, do you want to answer the discussion now? Okay, yeah, that's good. So before we get too off the middle of this philosophical discussion, I would like to see if anyone has a question for the academic board or our government representatives.
Thank you for the presentation. I got mathematical presentation. I'm trying to look at it because I'm trying and we have this thing cycling all articles and new articles at the same time in the same article. Are you going to do that? Your repeating your analysis in article level as well, or not? The age of the articles that are being cited in one article as a venue of citing.
I do hope to, at some point, The issue, I mean, I've been working on this since January, and that includes the time that I took using the generic parser to redo the entire database before CADRE was available. So I haven't had that much time. The problem sort of comes out of it just being such a huge data set. And so I am hoping the one that I am most likely going to try to do is to, and actually I have done this at some level, just looking at the sort of median citation age for each paper. So you're looking at things like median reference, median citation age, so that can show you if there's a big spread. But I'm hoping also to maybe just look at the spread from the youngest to the oldest reference in any paper, because that could show like there's a lot of papers in, say, some area that's 80 years and other areas are shorter. Once I start pulling in the Microsoft Academic Graph data too, there's slightly more fine-grained subject clustering in there than there is in the Web of Science data. So I'm hoping to use that to do various things, but to try to see if I can split this up more about like abstract algebra versus graph theory versus you know, algebraic topology. Yeah, and that'd be very interesting. The one issue, how many like straight pure mathematics papers have you like spent your time digging around in? So mathematics papers aren't structured in the same way as most science papers. A lot of times there's no method section, there's no discussion section. They just go and be like, well, here's this result. This is the thing I'm going to prove, and that's how they're structured. Which means that a couple of those would be absolutely fascinating, but the citation context one is sometimes a bit harder to drag out in mathematics. Oh, not by that, but if no one knows, at the University of Wisconsin, they have something called Deep Dive, which is an incredible full text subset, and that they can get you access to, and it has nearly 10 million full text, fully NLP'd articles already in it from all 4 of the major publishers and a lot of the, it's geodeepdive.org. And a lot of smaller publishers as well, and they are always looking to work with people, and the agreements that they have means that they can get access to that stuff even to people outside the University of Wisconsin.
We should get in touch with it.
Science. That was fine. Okay, so I about what are breaking up that from the other step. And I was thinking about the same course, which you have science as one long line. And I thought, you know what, you really break that apart, see what's under that. Yeah. What is contributing
Yeah, so that's something we're actually working on like right at this moment. Like I said, we only parsed the XML file 3 weeks ago. So we're putting together some graphs for this presentation, and like we hadn't divided all like science into each of the subfields in our data, but it should be done by now. So yeah, moving forward, we're gonna go more granular. So yeah, so I mean that's a big challenge. So for now, we're sticking with how the journals are classified by Web of Science. And so we have 3 different schemes. So prior to Web of Science, we worked a lot with JSTOR data. But JSTOR data is actually very social science heavy. So they're very broad strokes in science disciplines, but very granular in social science. So, you know, we just try to do a manual crosswalk between that and a paper in Nature that came out recently. The last author is James Evans. He looks at, him and his co-authors manually just divided Web of Science journals into like 13 different disciplines. So we have a version that's crosswalk between JSTOR and the Nature article category. So we should be able to impose that on our Web of Science data moving forward so we can get more granular.
I have a question for Charlene. I remember in your slides, you showed that you were able to build citation generations so deep. And I would imagine that's because your selection paper is relatively small. Is that the case there?
Yes. But only 4 generations of citations because the amount of citations will become very large.
Exponentially exploding.
And actually, one finding is that order and signal the difference for yeah, no need to go further.
All right. I believe you also represent the presentation in comments.
Yes, the day after tomorrow.
Okay. So check it out. I see we are about time, and let's welcome our host back.
Mostly I wanted to just reflect a little bit and think about the panel as a whole, the day as a whole, and how many people think you might be interested in using CADRE based on what you've heard? Nobody? Nobody wants to use CADRE? Oh, I can't see the hands. Put them up high. A few people. So I think one of the things that you're going to need to do is make sure they know how to register. So I'll just put a little promotion in there that we'll talk about that in the tutorial, correct? Yes. So please come to the tutorial. And if for some reason you cannot, leave us with some contact information. We can follow up. But I think you've seen some of the types of work that can come out of it. And some of the advantages. 2 of the presenters use both Microsoft Academic Graph and Web of Science. We're trying to get more data. I think one of the ones we're eyeing is the patent data set. So if you work with patents or you have any interest in that area, that's something else that's going to be coming on. And then hopefully into the future, and that's what, I think we got a little bit of a glimpse of what things might be like in the future. One thing is this whole idea of sustainability that was kicked off with this conversation and comments by Sam. The whole idea of what's the future going to look like, Connie's question about whether it's going to include our data providers as the service providers. I really do hope that we can attract more of those, not only the data sets, and we actually are having some conversations about more data sets right now, but also getting them in the same place will allow the researchers to use all those different resources in one place, which would be really convenient and it would really help cross communication across the field. So give CADRE some thought. Feel free to contact us now or at any point in the future. Panel, Val, Sharon, Kadi, did any of you or Tim have any more comments to add, or is there anything from the audience? Anyone have any other burning questions? Well, I did want to make one. Oh, Kadi does. I'm sorry. Oh, a photo. We want to have a photo. Thank you, Connie. We'd like to have a photo of all of our panel up here. So first of all, we need a photographer, and then we need everybody who is in the workshop to come up. But I did want to actually ask one more question. Challenge in the conversation. So I'll ask it later. I thought it might benefit the group. But so thank you very much, and we'll see you at the tutorial.